Okay, we can start our next seminar, the Smirnov seminar in PDMI. And our speaker today is Professor Itai Shafrir from Technion. Please.
Uh, Thank you. So first of all, I would like to thank the organizer, specifically Professor Lazarov, for this kind invitation. I'm going to speak some variational problem that I will explain about in a moment. It is a joint work with Dimitri Golovati from the University of Akron. I will speak a little bit about the physical motivation. So the original problem coming from the Landau-Degen theory for nematic liquid crystals, but in a limiting thin film regime. So somehow the problem becomes easier to handle, as you should see. So the original problem is set on a slab of width h, 2h actually, in R3. And when you study the limit as h go to 0 of the original problem, you get a gamma convergence to a two-dimensional problem. And this is what you see now, E epsilon of u. This is the energy I'm going to consider during the whole talk. So it is important to note two things. First, maybe I will tell just a moment about omega. So omega is in R2, is a smooth, bounded, simply connected domain. The maps I'm considering are vector valued. So it's actually taking values in C, in the complex plane, if you want, or in R2, as you wish. And you have epsilon here. So you have actually two terms in the energy. An integral on the domain, this is the first one, and an integral on the boundary of the domain, and this is this term in red. Epsilon is a kind of penalization. I will speak about it later on, but you're looking at the limit eventually when epsilon goes to 0. You penalize in the domain when the modulus is not 1. So in the limit, you expect to find the map taking values of modulus 1, that is to say an S1 valued map in the limit. On the boundary, you have also a penalization, and the term is this one. So you force I will speak about it later on also, but you want the angle between u and g to be alpha. This is what this term tells you, that because you penalize when it is not 0 here, and so you push it to be with satisfying the value g ei alpha or g e minus I alpha on the boundary. So you have two kinds of penalization, and they are not in the same force somehow, because you see here you have epsilon squared, here you have epsilon s with s less than 1.
Yes, I'm sorry, Itar. Is it
Yeah.
u in bracket ug? Is it u is vector?
Yeah. You get u if you're taking value in C. So either you look at it as in R2 or in C, and this is the real scalar product. G is also a vector, because G is the boundary condition. I didn't mention it, but in a moment, G is the boundary condition in some sense, although it is not directly boundary condition, but it plays the role of boundary condition in some sense. So G is given only on the boundary, but it takes value in S1. So it has a topological degree, and I will assume that the degree is non-zero because this is the more interesting case. So let us assume the degree is capital D, always bigger or greater than 1. Yeah. So
And
both U and G are vectors, actually. Yeah.
and alpha is also given.
And alpha is given. Yeah, exactly.
Okay.
Alpha is given. It could be pi over 2, which will be easier in some sense. It will be then just UG square, but it turns out that the more difficult case is where alpha is not pi over 2. Yeah. Now in practice, actually, in the original motivation, in the physical motivation, G is the normal to the domain. But since we are a mathematician, we consider also other cases. So you see, it's natural to say that you want to impose a boundary conditions that U on the boundary has a certain angle with the normal to your domain. This is in the physical model. But here we allow G to be any smooth S1 valued map. And as I told you, S is a given parameter. We assume that it's smaller than 1. It is also interesting to consider when it is bigger than 1, but we didn't study it yet. Okay, let me just, to give some context, let me describe previous works which are related somehow to this model. So a famous work of Betuel Brazis Elan from about 30 years ago, they studied the Ginzburg-Landau energy, which is actually the same term that we have here, but they don't have a boundary integral. Instead, there is a Dirichlet boundary condition, G. G is the same as before, but now we impose it as a strong boundary condition. And they studied, and many other people studied this model. I just mentioned a few names like Struve, Frank Boilin, Sandier, Mironescu, and many others. A slightly, or not slightly, less popular model, a variant, which is relevant to what I'm talking about. This is class of problems with weak anchoring. And here is an example. So it's not exactly the example I'm studying in the current talk, but it's a good case to consider in order to compare with the usual Dirichlet boundary condition. So here, in spirit, you also have a boundary condition G on the boundary, but you don't impose it as in a strong way, like in Dirichlet, but through this penalization in this integral. And the term to describe it is weak anchoring. It's not strong anchoring, like usual boundary Dirichlet. It's weak anchoring, so it's thus through penalization that you impose eventually in the limit epsilon to 0, you impose U equal to G in the limit. What happens with this model in contrast to the other one, although they look similar, because in both cases you have some energy, you have the same integral in the domain, but you impose the boundary condition in a different way. It turns out that in the second model, you might have boundary singularities, while in the first model, in the limit, you have only interior singularities. So there is an interest to study also this second model because it allows you to model other phenomena. And this was studied also with some people, like Moser Kurske, Alamar Bronsar, Galavaus Suosa, Ignat Kurtze, and others, not so many, but others. But specifically, what I described in the first slide was a version of it where instead of this, if you remember, there was a boundary integral, but it was with the product, a scalar product between U and G minus cosinus alpha. This is my term in our problem. So it's in the same spirit, but it's a different one. And this model was studied by, I know about two works, by Alamar Bronsar and Golovati, and Alamar Bronsar Mironescu that continued the original study. And I will refer mainly to these two works because this is almost the same model that I'm considering now. So let's go back to our model. So again, this is the energy I'm going to consider. It's a kind of a weak anchoring model, as I said, because you have an integral in the domain with a Ginzburg-Landau type energy with epsilon here, but on the boundary you have a kind of a weak anchoring, but you don't impose U equal to G, but in some sense you impose the angle between U and G to be alpha or minus alpha. Okay. And now let's give some intuition what we expect as epsilon goes to 0. So if we look in domain itself, because of this penalization, when epsilon goes to 0, you penalize whenever modulus of u is not 1 or far from 1. So in the limit, you expect to be modulus equal to 1. Okay, this is for the first step. From the boundary term, because of this penalization, you expect to, this one actually, again, so you expect that u epsilon will be very close to either g e I alpha or g e minus I alpha, yes? So you expect the limit in some sense of u to be something of this type. But here there is a topological obstruction. So let's start with the continuous case. So suppose that what you expect to find in the limit, capital U. So you expect to find a map in S1 value because of this penalization in the first term. And it should satisfy, because of the second penalization explained here, you expect it to be equals either to GEI alpha or to GE minus alpha on the boundary. But if you look at continuous functions or continuous maps, this is not possible. You cannot be an S1 valued map in omega bar satisfying a boundary condition of degree non-zero because of Brouwer theorem. So there must be 0 in the interior, and then it's a contradiction. But we are not considering in our rational problem continuous maps, we are working in H1. But it turns out it's a more complicated or involved theory, that there is also a kind of degree theory to the trace of H1 maps, that is maps in H1 half on the boundary, with values in S1. There is a well-defined degree, and you have the same problem as you have with continuous functions. You cannot find a map in H1 omega with values in S1. I say its values in S1, I emphasize, with degree non-zero on the boundary, like as the case of continuous maps. So you have a kind of a problem. So such a U cannot be the limit of U epsilon, of the minimizers for epsilon. So you still expect it to be SL valued, but necessarily it will have singularities because of this topological obstruction. They might be either in omega or on the boundary. So in omega, it means that it will come from zeros of U epsilon. And on the boundary, eventually it will be jumps between the two possible values, GI alpha or GE minus I alpha. I will explain it a little bit later. And as I said, the minimizer, before passing to the limit, the minimizer should have either interior vortices, which are actually zeros, or binary vortices, which are small arcs on the boundary where there is a transition between the two limiting possible values, GE minus I alpha and GE I alpha. And here is a picture. So here, there are actually two possible scenarios if I try to construct, say, an upper bound. I'm not claiming it's the minimizers, but say I'm trying to construct an upper bound for the energy. So I call these maps V alpha because the minimizers are U alpha. So V alpha are other maps that I construct myself in order to have some intuition and in particular upper bound for the energy. So assume for simplicity that the degree is 1. Okay, we have degree 1. So on top, we have one scenario for constructing a test function which will have eventually good energy, it won't cost too much, okay? So what we do, we choose a point, let's call it 0 here, and here inside the ball, a disk of radius epsilon, we let V epsilon to be equal to R over epsilon EI theta. So you see that on the boundary of the circle, the red circle here of radius epsilon, V epsilon is EI theta, with theta is computed with respect to the origin. And here you continue, in this annulus, you continue with EI theta. And now we are left with the domain between the domain omega and the blue circle. So, and we have a boundary condition here. Suppose we decided it will be GEI alpha on the boundary, and the EI theta as we constructed already on the blue circle. So yeah, we have a kind of an annular domain, and we have boundary conditions which are both of degree 1, the GEI alpha and the EI theta here. So we can complete it with S1 value, with a smooth S1 valued map. So the modulus will be 1 all the time. So what is the cost of the energy? So there are two terms, the integral on the domain and the integral on the boundary. Now let's look first on the boundary. On the boundary, there is zero contribution because it's GEI alpha. So the angle with G is all the time, the scalar product with EI alpha, with G, sorry, is cosinus alpha. So the boundary term doesn't give anything. You divide by epsilon s, but epsilon, 0 is divided by epsilon s, it's still 0. So all the contribution here comes from the interior. In the interior, computation shows that the energy will be of the order pi log r over epsilon. So the ratio between the r will be independent of epsilon, and epsilon eventually will become smaller.
What is E epsilon? Is it is it error of? So it is trace of V epsilon in the ball.
What you ask?
What is V epsilon? What is E epsilon?
V epsilon?
E epsilon. E.
E epsilon is the energy.
So it is whole integral.
It's everything. It's both integrals. But the second integral is 0, and everything comes from the first integral on omega. Not on.
It is only numerical observation.
This is actually computation, direct computation. Yeah, because you see what's going on here. You have actually in the small ball of radius epsilon, what you have. We are looking only on the integral on omega. Let me go back. We are looking at this integral. And now suppose omega is just the ball of radius epsilon.
I understood.
Yeah, you see, so gradient of u will be of order 1 over epsilon. So you get epsilon 1 over epsilon squared, but the area of the disk is epsilon squared. So it's just a constant. And here also, this will just order of a constant divided by epsilon squared, but the area of the little disk is also epsilon squared. So all the contribution from the ball of radius epsilon will be O of 1 for this term. Now we are left with the annulus. On the annulus, you have EI theta. So the energy, so this doesn't contribute anything in the annulus because the modulus is 1. So everything comes from here. So we have only to take into account the gradient of EI theta, which is like the gradient of theta in modulus, yeah? So, and gradient of theta is 1 over r. So you have the integral of 1 over r squared from epsilon to capital R, but you have the Jacobian r. So eventually you have an integral of 1 over r between epsilon and capital R. This gives you ln r over epsilon. And you have, because of the integral of the phase, you have also pi. So this is why you get this term plus O of 1. So this is one scenario. But this didn't use at all the boundary integral, because for the boundary integral we just let it be 0. But it turns out in some situations that maybe it's better to use the second integral and have less energy using another construction. And this is really what is called the Boojums. construction. So here we have another possibility. So the contribution from the boundary won't be zero this time, but it will be bounded. And most of the contribution will come from half annulus to half annuli near the boundary. So we decide on about 2 points where eventually in the limit there will be singularities, but boundary singularities. This is called the Boojums. And the construction is the follows. On the boundary, here on the black part, it will be G E minus I alpha all the way until this point. Here, it will still be between the half circle, the blue half circle, and the red half circle. It will be still E minus I alpha, but here it will pass in a smooth way to the other possible value, which is E minus I alpha. And all along here, all along the circle, on each circle here, it will go from E minus I alpha to GEI alpha on each circle here around x0. And here you will complete it in some way, which won't cost a lot. And once you get here, you do similar thing, but here you go from here you are EI alpha, but on the other side will be EI 2 pi minus alpha, which is it's actually the same as GE minus I alpha, but the change of phase on each of these circles will be 2 pi minus 2 alpha. Why? Because you move from GEI alpha to GEI 2 pi minus alpha. So the change of phase is 2 pi minus 2 alpha here. While here it was between minus alpha and alpha, which was 2 alpha. In any rate, when you do the computation, which is actually very similar to the computation here, most of the energy actually comes now, not from the interior, but from the two semi-disk, more or less, here that you have, the two half-disk, and each one of them gives another contribution, and the contribution are given here. So it's the same order of contribution. It's ln R over alpha, but the coefficients are different, and they depend on S and on alpha because of this expression. So here it's alpha because you're moving to alpha here, and here it's pi minus alpha because you are 2 pi minus 2 alpha change here.
Excuse me.
It's difficult a little bit to catch it in first sight, but it's very elementary.
And what is if alpha is equal to 0?
We are not considering alpha equal to 0 here.
So,
but we are not considering it here because then, no, you don't have this jump. No.
Well,
Yeah.
in principle, it is possible.
But it is possible. It is possible, but then you should modify a little bit the construction, etc. But we are looking at alpha is strictly between 0 and pi in our model. Yeah. Now, okay. So as I said before, there was already some work on this model, and this was our motivation, in fact, the work by Alama, Bronsar, and Golovati. They studied almost the same problem, yeah? But you see what is the difference. In the boundary term, they don't have only the red term that we described before, but they have an additional term, which looks like a Ginzburg-Landau potential, but on the boundary. Like the same terms that you have here in the integral on the domain. Why did they put it? it turns out that it is not part of the physical model, but they, in order to carry out their analysis, at some stage they saw, okay, we don't know how to deal with this energy, there's some problem here, so they introduced this additional term for technical reasons or artificially. It is not really justified by the physical model. And so this is what was one of our motivation to see what's going on here. Is it really needed in order to carry out the analysis to look at this term? Let me to add this term. So we want to do without it. Let me just mention that what I showed you in the previous slide with the figure, this upper bound construction, it is valid for both models. It doesn't see any change in it because actually in the Boojums scenario, in the second one, the modulus is always equal to 1 on the boundary, so you don't use it, doesn't have any significance. But in practice, when you study minimizers, it turns out that there is some issue that adding this term helps to control what's going on. As I said, it's not part of the physical model. So let me just mention the main theorem of Alama-Bronsard-Golovati. So there is this constant. Maybe you remember that in the upper bound that I showed you before in the slide with the figures, this term actually appeared in the second scenario when you had Boojums. So there are two scenarios, and they depend on the value of S and alpha in the following way. If the product of S and C alpha is bigger than 1/2, then what they prove that you will have only interior vortices in the limit. And this is what they say, that you have D points, D is the degree of the map G, exactly D points, this will be the singularities in the limit, such that U epsilon n, so a subsequence of the minimizers, U epsilon, will converge away from these points to the map U star, and U star will be a singular S-valued harmonic map that satisfy one of the two boundary conditions, either EI alpha G or E minus I alpha G, as we said. So it's very much like what happens in the usual Ginzburg-Landau model when you have a Dirichlet boundary condition and you have D singularities in the interior. And the energy is also like in the Ginzburg-Landau case is pi D ln epsilon plus O of 1. In the previous slide, when I showed you the upper bound, in the first scenario, D was 1, so it was pi ln epsilon. It's exactly this quantity. Now, the other scenario is actually the Boojums scenario. So if SC alpha is strictly less than 1/2, then you have the Boojums scenario. So you will have in the limit singularities on the boundary. The number will be 2D, 2 times the degree, because they will come in couples. As we saw in the previous slide, I had to put two points on the boundary with jumps in the limit. And the convergence again away from these points to an S1 valued harmonic map, but which will have a different profile. And on the boundary, the map will have jumps, so it will be either GI alpha or GE minus I alpha, and there will be arcs. So on the arcs between, say, zeta 1, zeta 2, it will be GEI alpha, and between zeta 2 and zeta 3, it will be GE minus I alpha. So there will be a discontinuity, a jump discontinuity of the boundary value on the boundary. And the energy this time will be this thing. So you see again, SC alpha white is interfere, because if you see that when you compare the two quantities, you see exactly when one is bigger than the other one. If SC alpha is bigger than 1/2, then the second energy is bigger than the first one. And when SC alpha is less than 1/2, it will be smaller, and so the second scenario will happen. Okay. Of course, in the case of equality, there is between SC alpha and 1/2, there is also equality between the two possible energies, and then the actual minimums will depend on more refined analysis. It will depend on the O1 terms, and this is something we didn't investigate. So what we want to do is to derive, we have several contributions, but the first one, the main one, probably, obtaining the same result as Alamab-Ronsard-Golovati for minimizers of the real energy, this one that I showed you at the beginning, so without the additional term, the boundary condition, the boundary integral of this type that they added on the boundary.
It's a very naive вопрос. The question is the following. I want to ask, sorry. For example, if I will consider UG equal cosinus alpha on the boundary, then it will be just equal 0.
The second term, exactly.
Equal 0, and the U on the boundary will be equal G, and the solution it will depend. Okay, thank you. Thank you. So
essentially, the minimizers in the second scenario, in the Boojums scenarios, they will do essentially this, not exactly, but you will be, sorry, in the first scenario, you will be essentially GEI alpha, say, and this contribution will be almost 0. Maybe not exactly 0, but almost 0. Yeah. Now, this was the first thing. The second thing that we were able to prove, which is relevant also for the Alamab-Ronsard-Golovati model, which is essentially the same, is that we have the modulus of U epsilon will converge to 1 uniformly on omega bar. So there will be no zeros at all, something that was left open in previous works. This is in the Boojums scenario. Of course, in the other scenario, it's not true because you will have zeros in the limit. So, of course, it's not true. But for in the Boojums scenario, when SC alpha is less than 1/2, this is what happened. And finally, a subsequent work to the one of Alamab-Ronsard-Golovati was Alamab-Ronsard-Smirnova, and one of the results there that we studied they got a very precise description of the behavior of the minimizer near the Boojums, but it happened only to half of the Boojums. The light one, when you pass from minus alpha to alpha, not in the heavy one, when you pass from alpha to 2 pi minus alpha. Okay, so I will talk a little bit about it later. So what are the difficulties that we encounter when trying to do this, to obtain the same result as the Alamab-Ronsard-Golovati when we don't have the extra term, this one, yeah?
Itai, one question more. Alpha is less than pi or than pi half?
Sorry, pi over 2. Sorry, maybe I said pi.
Cosine is positive. Cosine is positive.
Yeah.
Okay.
Yeah. Maybe I said it 1.2 pi. I mean between 0 and pi over 2. Yeah.
Okay. Thank you.
Actually, the case pi over 2, when actually you don't have cosinus alpha because it's 0, was studied before, and it was somewhat easier. Okay. So one of the first difficulty is one of the really the basic estimates that you need in order to start working on the problem. So although you expect it to be true, but how do you know that the minimizers, U epsilon, are bounded in L infinity uniformly in epsilon? You must have it in order to start any analysis, yeah? And it's intuitively, it should be true because you don't see any reason why a minimizer should go and have a big modulus, yeah? But you have to prove it. And it turns out that in this model, there's some difficulty in proving it. And this is one of the things that worked easier for Alamab, Ronsard, Golovati by adding this term. Let me explain why. The usual way to obtain such an estimate is a kind of a greedy argument. You take U, and suppose you want to prove it is less than 2 in modulus. So you use radial projection of the map on a ball of radius 2 around 0. And you show that the projection of the map has less energy. This is a way to prove it. So let's try it. So how it affects the different terms in the energy. So let's start with this one. You have it in the integral on the domain already. This is the in the Gainsborough-Landau potential, yeah? So this, of course, will decrease. If you have modulus, say, 3, and you project to 2, you will decrease the value of this thing. So it decreases it. What about the energy itself, the Dirichlet term? So pointwise, the gradient, the modulus of the gradient is, the norm of the gradient will be smaller. It's easy to see. We are left with what you have in the boundary integral. Now, in the Alamab, Ronsard, Golovati model, on the boundary, you have integral of this thing, well, divided by epsilon power s later, but whatever. And it turns out, okay, so here if you project, so you replace little u by capital U, which is the projection on the disk of radius 2, this term will decrease, as we mentioned before. I mentioned it before, but this one, not necessarily. But if you do computation and you compare how much you gain by this with how much you might lose in the other term, it works okay, and actually the sum is decreased. So it works. So this greedy argument works just by projection. And so by projection, you can show that the modulus of U epsilon is less than 2. This, now coming back to our model and trying to do the same. So for the integral on the bound on the domain, no problem. The gradient term will decrease, this term will decrease. But we don't have this term anymore. So sorry, we don't have this term. We have only this term on the boundary, and this term doesn't necessarily decrease when you project. So we need something else. And the question is what happens in our case, where you have the boundary term is this one, and projecting doesn't seem to work here. Now, actually, we tried a little bit and couldn't find a solution for some time, and then I asked Nazarov. It's not the same Nazarov present here. It's Fedya Nazarov, which is in Kent State, and he provided us a solution, which I found very elegant, so I want to describe the main steps in his argument. So the claim is that...
By the way, he also is from St. Petersburg originally.
And it's also from St. Petersburg originally, I know, yeah. But not family related to you, I guess, no?
No.
No, but yeah, but still Nazarov, it's... Nazarov are strong, it seems, in mathematics, all of them.
Surely.
All the ones that I know. So let's see the argument of Fedya Nazarov, the main step. So first he proposed to something very simple. consider by P some smooth extension of the function gx, of the vector function actually, gx cosinus alpha to omega bar, because originally G is defined only on the boundary. So this term is not defined on omega bar, on omega, but use some smooth extension. How it helps you? The terms that you are involved with in the boundary integral, you see this one, U scalar product with G minus cosine alpha, you can write it also like this. In some sense, because you see you have UG, and the scalar product between P and G, because of this definition, is cosinus alpha, which is okay. So in some sense, you change the origin from 0 to P of x in this. In a moment, I will show you a picture. Now, you still use projections, but we don't decide for the time being what is the radius, but suppose we're taking radius t greater than 3, and for simplicity of notation, from now on, instead of u epsilon, we'll denote it simply by u, and we denote by ut the projection of u on a ball of radius t around the point px. Here is the picture. You have ux, here you have px, you take a disk of radius t, and you project u on, whenever, of course, when your map is inside the ball, the projection is the same map, but if you are outside this ball, you project to the ball of radius 3. And you get to this point, ut, which will be on the circle in this case. And we look what happens to the energy, the different terms of the energy, using this projection, okay? So first thing, in the domain, you have the integral of u square minus 1 square. Yes, the usual Ginzburg-Landau potential divided by epsilon square, whatever. Since the modulus decrease, you can see here that the distance from 0 decreases because of the projection. These terms become smaller, so it works well. Let's look on the boundary. Now, in the interior, we have also the Dirichlet energy. I will talk about it later. But let's move to the boundary. On the boundary, you have this term, yeah? So you have to look at this term, utx gx minus cosinus alpha. Now, this term decreases, you see, because you take, you look at ux, because of this representation, actually, you see, this one. So you actually have to look at ux minus px, so this is this vector, multiplied by g. When you replace u by ut, you have utx minus px. So it's in the same direction, and you again multiply by g. So since it's in the same direction, but it is a smaller vector, you just decrease it in absolute value. Yeah. So it's also decreasing. So for two terms, it works well. Now, what happens in the integral of the domain on the Dirichlet energy? This is not good. No reason it will be smaller than the gradient of u. But let's see what happens. So when you take a point where u of x is outside this disk, and you do the computation and you compare the two terms pointwise, you get this inequality. So the best would be if it was just gradient of ut square in norm less than gradient u square. It's not true. You get it's less than this term, but minus this term plus some c square. So I would say, I'm not Nazarov, so I would say, okay, the method doesn't work, what can we do? But Nazarov had another reasoning, and he said, okay, let's continue. We know that u is a minimizer, because u is u epsilon. So its energy is less than the energy of ut. So if you plug in this inequality inside, you conclude that actually the energy of what you have here in minus sign, the energy of the norm of u minus p, should be less than the energy say, the integral of C squared, because otherwise you will get a contradiction to the minimality of U. So you get a kind of an inequality. That the integral, let's just remember that V, from now on for simplicity, I denote by V the distance between U and P. So on the set where V is bigger than T, the Dirichlet energy of V is less than 2C squared, the measure of the set where V is bigger than T. So we are not going to use this inequality. There is another inequality that Nazarov proposes to use, and this is a kind of a Poincaré type inequality, that for maps in H1 omega whose support, the measure of support is less than A, you have this inequality, a constant time, so the integral, the L2 norm of V, of W is less than a constant times A, where A is the measure of the support, times the Dirichlet energy of W. The truth, I admit I didn't know about this specific inequality, but it's quite easy to prove, a Poincaré type inequality. And what he's doing next, I won't give the details, but I will just tell you that he's using an iteration like the Giorgi iterations for obtaining L infinity a priori bound for solutions of elliptic equations. So these are the kind of iterations, and choosing a sequence as Tj. So he starts, say, T0 will be the first T that we took here, and then he will choose by recurrence T1, T2, and T3 in such a way that the series sigma Tj will converge, and the measure of the set where V is bigger than the partial sum between 0 and k of the Tj will go to 0, which will mean that the set where V is bigger than T, where when U minus P is bigger than T, is 0. This means that actually U itself must be bounded by T plus 1, say. Yeah? Now, I want to do the details of the iteration, just mention to you the relation to the Giorgi. For those of many of you, I guess, know the method. So there are two elements in the Giorgi method. There are two inequalities he's using. One is Cacciopoli inequality that somehow bound say the L2 norm of the gradient by the L2 of the function itself. This, in some sense, the first inequality, in some sense, is analogous to this because it's somehow you bound the Dirichlet energy, but something which is related to the V itself. It's the second inequality that the Giorgi is using is Sobolev inequality, where you bound, say, the LP norm of U by the LP norm of the gradient. Here you see something of this sort. It's not Sobolev, it's Poincaré, but in the same spirit. So I would say that at least from the philosophical point of view, you can see why we can use these inequalities in the same spirit as the Giorgi in order to obtain the bound. So this is the Nazarov very important contribution to us, just in order to be able to start working on the model, because we didn't know how to have an L infinity bound for the minimizer. Now the second difficulty, which is actually the one that was mentioned by Alama, Bronsard, Golovati as a reasoning why they added the additional term on the boundary, this one that they added, which is actually not, now I'm going to show it's not necessary. So a main tool, now in Ginsburg-Lambert theory, I don't know how many of you know it, but it's quite technically heavy analysis with bed disk in order to locate the singularities and zeros and so forth. I don't want to get to the details, but just tell you in principle that you have your minimizer U epsilon and you want to locate the bed points. What are bed points? Bed points are when the modulus is far from 1, and this is the first set is this something of this type when the modulus of U epsilon is bounded away from 1, This is a technical issue here with the a square root of 2. A is some positive number. And the second thing, in our case, you are worried about is the point on the boundary where U is not close neither to Gi alpha nor to Ge minus I alpha. So you see it in the term W tilde here, although W tilde C also when on the boundary you are far from 1 in a similar way to this, because you have the additional terms. Okay. And the bed disk, and what one can show is that the bed sets, which contain these two types of bed points, can be covered by a finite union of disk, where this disk can be either interior bed disk, and then there will be of radius of the order epsilon, so k epsilon, and the center is in omega, or boundary bed disk. And in this case, we will take the radius to be of the order epsilon to the power s. And the center of this disk, essentially bed disk, half disk, because we intersect with omega, so the centers will be on the boundary. And this is kind of a picture. So the first type of disk, these are the blue ones. So they will cover the points where the modulus of U epsilon is strictly less than 1. And the boundary bed disk, which is actually half bad disk, will be something like this. And they will correspond to points where on the boundary here, U is not, the angles that U does with G is far from alpha or minus alpha. And eventually what one has to do is to get in the convergence proof, a large part of it is a lower bound for the energy, and you need to compute lower bounds for the energy of annulus of this type in the interior or half annulus of this type near the boundary. And especially the difficulty arises in the half annulus of this type. And what Alama Bronsar-Golvati proved for the energy of half annulus of this sort between inner circle little r and the larger outer circle capital R, something of this type. So again, it's a multiple of ln of capital of the ratio between the radii. I want to explain exactly what are the...
Вторник я не буду ходить на спецкурс.
Sorry. It was not for me. Okay, so there is some n is some integer measuring what is the change of phase around this point. I don't want to get into details, and tau is another parameter. Just to give you some to taste the issue, it's not very important here. But what is important here is that in order to get this important estimate, Alama Bronsar-Golvati needed to know that on the boundary, this is what I denote by capital gamma little r. Capital R is the two segments of this, of all the points around, say, the point x0 on the boundary, which distance between little r and capital R. I will say that in the picture, we are talking about these two arcs, this one and this one, assuming here of the radius r and little r, and this is capital R. Yeah, so we're talking about boundary integrals on these two arcs, and they needed to know that this quantity is small. Now, this quantity is very related to the terms they added to the energy, and indeed this is the reason why they added it, because once they added it to the boundary integral of the energy, they managed to control it using positive identity. But in our case, it's not present in energy, so you don't have an estimate for it. Now, what we were able to do is to prove a global estimate, in particular, implying the ones they needed, because we have it on all the boundary. We know a priori to show that this integral going to 0 with epsilon on the whole boundary, not just on some part of the boundary. So, and this resolve all the problems Alama Bronsar-Golovati had with the model. So this allows us to avoid adding this, where I wrote it, without this term on the boundary in the energy. Yeah. And so let's show. I will show because it's just one slide, very elementary proof of this estimate that we can prove a priori in the beginning of any analysis. So here, the proof of this inequality. So the trick is the following. We fix a smooth vector or C1 vector field, taking value in the unit disk, such that it is equal to nu of x on the boundary. Nu is the unit outward normal. You notice that if you define capital G in this form, it will behave like 1 minus t square. So especially it's important to see what happens near 1. And so near 1, it will behave like this term. And as long as we stay on a bounded interval until m, we will have this relation. And the idea is the following. It's very similar to the people that know in the scalar Ginsburg-Landau type energies, there is what is called Modica trick. So it's very similar to Modica trick in the sense that we are just using Cauchy-Schwarz inequality and something almost nothing. So let's start in the beginning. What about the first inequality? Look, on the right, we have the integral on the boundary, but actually just part of it, not on the boundary, in the domain. This is the Ginsburg-Landau energy, but we're just looking at the energy, at the Dirichlet energy of the modulus of U. So it's smaller even from the full energy. And the full energy is bounded by C log epsilon by the a priori upper bound that I essentially proved to you. So we have this inequality just from the upper bound to the energy. Now we use Cauchy-Schwarz inequality. I don't know how to call it exactly because it's just the elementary inequality is that a squared plus b squared is bigger than 2ab. Yet in a pointwise manner, this is what we have here. Yeah. Okay. And now this is why we introduce G, like Modica actually, that we notice that this term is actually the gradient of G in norm, calculated at the point modulus of U epsilon. Yeah. So because by the chain rule. So this is the beginning of the. Next, we say, okay, if we have this integral on the domain, it will be bigger if we just take this vector here without the norm and multiply it by v, which is a vector field with modulus smaller than 1. So of course we have an inequality. But now we can use Green theorem, use integration by parts, and we get that we have the integral of the minus divergence times this function plus a boundary integral. And next, we say the following. This integral, in a moment, I will relate it to the terms in blue, but this integral is the term I want to bound, actually, because of this inequality I want to prove. Okay, so this thing is less than C, the integral of the same thing, G modulus of U epsilon, because of this relation I mentioned before. And now I'm using what the inequality I got here. So multiply everything by epsilon. So it's less than C epsilon log epsilon because of this, plus C times the integral I get from here, the divergence of V in absolute value times G. Now, because divergence of V is bounded by constant and G behaves like 1 minus the norm square. We have this inequality. But again, because of the upper bound for the energy, this is just part of the energy, but without dividing by epsilon square. So it's less than C epsilon square log epsilon again. So everything is less than C epsilon log epsilon. So we got that this integral is less than C epsilon log epsilon. Just divide by epsilon power S, and you are getting the inequality we wanted. And since S is less than 1, this goes to 0. And this is really what we wanted to prove, okay? And this is actually resolved the second main difficulty in avoiding the Ginzburg boundary terms that Alamab-Ronsard-Golvati added. And using this already, we can prove the optimal lower bound for our energy. Even before proving the convergence, that's showing that it has the right behavior in terms of energy. So we need upper bound and lower bound. Upper bound is the same as Alamab-Ronsard-Golvati. The difficulty is with the lower bound. But now we can count on their energy. In their energy, they proved a lower bound for this. So here you have this W tilde with this additional Ginzburg-Ladron energy, and they proved the lower bound. But in our energy, let U epsilon a minimizer for our energy, which is the same as theirs, but we subtract the additional Ginzburg-Ladron term here. Then, since we can count on the lower, now the energy of the
I'm sorry, is it U epsilon is equal V epsilon?
V epsilon?
Understood. No, sorry.
Yeah. I will tell you in a minute. It's very easy. The energy V epsilon is the minimizer for the ABG energy.
Yeah.
So if you compute the ABG energy of our minimizer for our energy without additional term, so its energy is bigger, it's least bigger or equal than the ABG energy of their minimizer.
Yeah.
But what we subtract for our minimizer, we know now it's little of 1. So we get that our energy for our minimizer is bigger or equal than ABG energy of ABG minimizer, minus little of 1. But they already computed what is the optimal lower bound for the ABG minimizer. This is this one, depending on the two scenarios, yeah? So we could just get the same thing for our energy. So just from what essentially I proved to you, we already get the right behavior of the energy in our model, which is the right physical model, just counting on what Alamab-Ronsard-Golvati did with their energy and the additional estimated I showed. The convergence, it's another story. But I don't get into details, but we managed to do it because of this estimate I showed you a little while ago. There are two additional things I wanted to mention that we did, but I don't have time to describe. I think it's already quite more than an hour. So let me just mention that one thing we showed that in the Boojums scenario, when SC alpha is less than 1/2, when we expect Boojums, U epsilon in modulus converge to 1 uniformly on omega bar. I wanted to show you part of the proof, but I will skip it. And another thing is about the profile. I'm missing an E there, because there is a second work I mentioned, after Alama Brossard Golovati, there was a second work by Alama Brossard and Mironescu when they studied the asymptotic profile of U epsilon near a light Boojum after doing some blow up in epsilon s square. And it was a nice result actually that they showed after doing the right scaling, you see it converges to G at some point, EX psi, and psi satisfies some, is a solution of some Neumann boundary, nonlinear boundary condition for harmonic functions. And it turns out that Cabré and Solá Morales studied this type of problems and characterized under some conditions. These are problems on half plane, sorry, we are not two. Half plane with Neumann condition on the boundary. And so they prove that actually the solution after rescaling converges to a map with a phase satisfying this condition. And now we are able to do it not only for light Boojums, but also for heavy Boojums, because the main thing in order to start this story was to know that the modulus tends to 1 near the boundary at least, and this is, now we know it's true anyhow. So I think it's a good point to stop, and thank you for your attention.
Okay, let's thank the speaker. Please, comments or questions? No, it's very interesting. Thank you. Okay. Please.
Thank you very much. I will stop sharing, and or you can stop sharing with me, or stop sharing. Yeah. So it was a pleasure to be your guest. Maybe sometime in the future, more physical connection. Yeah.
Okay, thank you.
Thank you very much.
Excuse me, I want to ask one question.
Yeah.
Is it possible? Not even the question, but the comment. You consider the case when your map G is have a positive degree, yes?
Yeah.
In the case of negative degree, is the same.
Sure.
It reduces, yes?
Sure. We just, for convenience, choosing one sign.
By conjugation, you might consider conjugation.
The same thing. Yeah, you can actually.
So actually consider the case when G have non-zero degree.
Sorry.
And what you can say when G have 0 degree? This case is simple, I think. Yes?
Because it's simpler, because when G has 0 degree, it has a lifting. You can write it as EI phi, say. And then there will be convergence. So then you can have on the boundary, you can be GI alpha all the time, and you can complete with S1 value also in the interior. So there will be no singularities, not in the interior. The energy will not blow up. Here, what you see, the energy behaves like C log epsilon. It goes to infinity. In the other case, it will remain bounded, and it will converge to a smooth harmonic map, but without degree, without any problem.
No singularity in this case.
No singularity, yeah. So we are looking, and actually in the physical model, G will be the normal, so it will have a degree. So it's also the interesting case for the physical model.
Degree 1 in this case.
Degree 1 in this case, yeah.
Yeah, I have one more question. What about the case when omega has holes, is not simply connected?
Yeah, I believe it can be done, because for the original Dirichlet problem like between Bosé-Celan, eventually it was done later on, and I believe it can be done, but needs to check indeed. Yeah.
So it seems to me that the estimates, the key estimates, does not require this simply connected domain.
I'm not sure which, if it is needed. For a specific estimate you're thinking about?
No, no, for example, the estimates of absolute value.
The thing of Nazarov, I don't think it's really needed. Of course, when you have like an annular domain, you ask, say one hole, yeah? So you have 2 degrees in the outside and the inside. Now, if they are the same degree, actually it's like the degree 0 case, because actually there will be no singularity. If there is a difference of degrees, at least from my experience from the usual Gibbs-Bolander energy, it can be done, but of course, I believe it can be done without.
I see. There are global problems which are connected with the topology, and local problems such as estimates. And I think that at least the estimates do not depend on.
The estimate do not depend. Yeah.
Okay. Thank you once more.
Thank you very much. Goodbye.